Hello, welcome to the fourth lecture of nonlinear system analysis. Today we are going to see some definitions about stability of nonlinear systems, some mathematical expressions, and maybe if time permits, a method to find a linearized version of a nonlinear system. Okay, so let's start. So stability in terms of any system can be defined in these two notions. Okay, so first is for free systems to be stable. Free system means the considering that they are having zero input. Okay, for zero input and any initial conditions, the resulting trajectory should uh, should converge to a equilibrium point. Okay, this equilibrium point was also called as singular point in the last lecture. Okay, the next one is for force system to be stable. That means there is a certain input to that system. With bounded input, the system output is bounded. Okay, so there are two ways that we can determine the stability of a system. One is put initial condition as any value and input as zero, and then check whether with respect to time that system goes to equilibrium point or not. Okay, this is one method. And another is if you apply the input, if input is bounded, output should be bounded. Okay, so this is general notion of stability. In case of see, these are equivalent to LTI system, and unfortunately in nonlinear system there is no correspondence between these notions. Okay, so it could be that a system is stable for this arbitrary initial condition, but it is not stable for a particular input, or vice versa. It could be stable for this, it could not be stable for this. So they are unrelated in case of nonlinear systems. Okay, so it is simpler in case of nonlinear system to speak of stability relative to equilibrium state rather than using the term that stability of the system. So when we say a system is stable, uh, that can be claimed in terms of the linear system. In case of nonlinear system, you cannot say system is stable. You can say that the system is stable around this equilibrium point. Or a better compact version of saying is that the system, no, not the system, the equilibrium point is stable. The equilibrium point, let's say 1 comma 2 is stable, or 0 comma 0 is stable. That you can say, or unstable if it is unstable. So the stability, when we talk about stability in nonlinear systems, we talk about stability of equilibrium points or singular points. Okay, not the system, the whole system. All right. So consider as autonomous system. Autonomous system can be expressed by x dot is equal to f of x. Assume that the system has only one equilibrium point. For sake of simplicity, we are assuming that it has only one equilibrium point. There could be multiple equilibrium points also. Okay, we'll not go into that yet, but we'll see that in the next unit. Further, without the loss of generality, let the origin of state space be taken as the equilibrium point. For making it even more simple, we assume that the equilibrium point is origin 0 0. Okay, so there is only one equilibrium and that is origin. So what we want to check now here is that as time progresses, whether that system trajectories reach at that origin. Okay, so the system 8 is stable at origin if for every initial state x of t0 which is sufficiently close to origin, xt remains near the origin for all t. You may write down this definition. Okay, write down this definition. I will repeat the statement, or if see, this is very easy to understand. It is written in a simple language. The system is stable at origin if for every initial state that is sufficiently close to origin, xt remains near the origin for all t. Okay, so let's say that region is a circle of radius 3. So if all the initial conditions remain in that circle and they converge to origin anywhere in that region, if you pick up any initial state and all of those converge to that point, so we can say that it is locally stable. Okay, or stable. Generally we say stable. when we say stable, an equilibrium point is stable, it is referred to as locally stable. Okay, so this system is locally stable at that origin in that region of radius 3. Okay, that is the meaning of this. Okay, then next one is, it is asymptotically stable if xt in fact approaches the origin as t tends to infinity. So what we talked about, stable means that it is remaining in that circle. It is not leaving that circle of radius 3. Okay, it is remaining in there somewhere. Let's say that it is maybe spiraling, it is doing some circular trajectory, elliptical trajectory, or anything. It may or may not reach the origin as t tends to infinity. But if it tends to if t tends to infinity, then xt tends to 0, the origin equilibrium point, then it is called as asymptotically stable. Asymptotically, this term you know. Asymptotically means what? Asymptotically approaches means as t tends to infinity, that one thing coincides on top of another. Okay, this you know very well. What is the meaning of asymptotically? Then one more definition is there. It is called as asymptotically stable in large. Now this in large is a word. Okay, this is also called as globally stable. Okay, so it is asymptotically stable in large if it is asymptotically stable first for every initial state, regardless of how near or far it is from the origin. So we considered a region of radius 3. So if that region is very large, okay, let's say 100, radius is 100, or no radius in particular, it is like we say that means it is stable for any point you take on the plane. Okay, any point you take as the initial condition for that system, it will uh, cover a trajectory, it will take a trajectory, and it will go towards the origin. Then it is called as asymptotically stable in large. Okay, have you written this down? I will give you 1 minute. Please write this down. These three definitions. These are very important. These are important in this unit also, in the next unit also. Okay. So write them. Write them down. And these are very important concepts. If you don't understand anything, even a bit, please ask. Okay. I will not be able to clear your doubts if you move from this ununderstood. Like if you don't understand this, and then you come again 10 days later and ask, then I cannot explain that to you. Okay, this is very important, because everything uh, that we are going to learn after this is based on these three definitions. Okay, have you written this down? Say yes. If you have written this down, say yes. If you are writing it, we will wait. Okay. So 1 minute has passed. Is it done? Yes. Just these three definitions you need to write. Okay. The system is stable at origin if it is asymptotically stable in large. This in large word is important. In large, asymptotically, and only stable. Okay. So I think 1, 2, 3 is done. Okay. Now those definitions are, see, these are definitions written in word form. Okay, so how do they how do we express them into some mathematics? Okay, what does it mean mathematically when we say that this statement is true? Okay, so see, the system is stable at origin if for every real number. See, I'm just rewriting this equation, this sentence in with some mathematical notations. Okay, see, for every real number epsilon, there exists a real number delta that is dependent on epsilon, such that, see, x of t0 is inside a delta, is bounded by delta, we can say, and x of t will remain bounded in epsilon for all t. So what does this mean? This may look complex, but this is nothing but this. Okay. See what we considered a radius of 3, right? So we pick any initial point from a circle of radius 3. So that 3 is nothing but, see here, delta. Okay, that is delta. So the distance of x of t0 from origin, this double pipe, is called as the norm. Okay, 2 norm or Euclidean norm. It is used to determine the distance of that vector from the origin. Okay, if it is represented like this, it can be, see, it is x1 square, x2 square, and that. Okay, so you can find it out because we are plotting it on coordinate system x1 x2 graph. It will be x1 square plus x2 square. Okay, so initial condition, for all initial conditions you can find a Euclidean norm. That is basically the distance of that point from the origin. So when we say that delta is 3, then any point that we choose inside that circle will satisfy this. Okay, that is the meaning of this basically. So if we have an initial condition such as this, results in all x of t inside another circle epsilon. Okay, another circle. It may be 2, it may be 4. Okay, it is not necessarily that it is less than 3, but there is a definite circle. Even it could be 30. Okay, you start in the 3 circle of 3. You may go outside and settle inside a circle of 30, but it is definite that you are settling inside a circle epsilon. Okay, then that system is called as stable. And this is the definition of, we can say that, see, for a particular initial condition, the output was bounded. Yeah, bounded by this circle of epsilon. This you can see in this diagram. See, this delta is the initial conditions region. So you choose any point from this, any point, you choose any point. It will go and remain in the circle of epsilon. This S of epsilon is sphere. S is denoted, S is just we are using as a notation for denoting its enclosure by that epsilon. Epsilon is nothing but the radius of that circle. Okay. So if we start from the circle of delta, we move and remain in the circle of epsilon, and we remain in that. Then it is called as a stable system. So this is a stable systems diagram. Okay, this definition. Now this we are looking ahead. This is we can say that premonition or that thing. The Lyapunov chapter is the next one, unit number 5. But this definition is similar to the Lyapunov's definition. This definition for Lyapunov uses concepts of vector norm. Okay, so this, see, the vector norm is denoted by this. It can be found out like this. Okay, Euclidean norm. It is also called. So this x less than r determines a spherical region. See, if it is nth order, then it is nth order sphere. Okay, we know that second order is a circle. Second order plane, it is a circle. In third order plane or third order space, it is a sphere. In fourth order, we don't know what is that shape, though. So that shape is called as hypersphere. Okay, you don't need to worry about that. We are going to consider only second order system. So it is going to be a circle. This is a circle. So for any circle of epsilon that we may designate, the designer must produce a circle of delta, so that the system initially in a circle of delta will never leave circle of epsilon. See here. So what we saw, like, this is a circle of initial conditions. From that, this will not leave. But the problem for the designer is that epsilon is given, that you wish that system should be inside this circle of epsilon. Okay, that is desired. So you need to dictate, like, what should be the initial condition. So you need to find out this circle of delta. So that is the designer's problem, to find such initial conditions for which the system is stable. Okay, so this is 18a, this figure. Okay, this was the definition for stable, the first definition that you have written down. Now the second one is Yeah, okay. Second one is another definition, but yeah, we can consider that. So consider a second order linear autonomous system whose phase trajectory is 17b. Let's see. 17b is this. Okay. So center point we are considering. If yeah, so center point, you know that it is it moves in a circle. It does not go to zero, or it does not leave that circle. For a specific value of epsilon, we can find the closed phase trajectories whose maximum distance from that curve to the origin is epsilon. Okay, that whatever, if it is ellipse, then the larger radius is epsilon. Okay, we then select a value delta which is less than the minimum distance from the curve to the origin. Now what is this minimum distance? That if it is ellipse, the shorter radius we take, and we take a delta less than that. The delta of epsilon, delta depending on epsilon, so chosen will satisfy the condition to guarantee the stability. So this is a design procedure that we do for a particular system. So, so for a figure, figure 15 was you have drawn this. I think it is saddle point. For saddle point, the system is unstable. You know that this is unstable, right? This, okay. The equilibrium state is not stable since for given epsilon, a value of delta can't be produced to satisfy the condition of the definition. Okay. So what is the problem with this? See, if you draw a circle, none of the trajectories will leave, stay in that circle, right? They're going to leave from this end or this end. So this is going to be unstable. It is impossible to find it out. For this, can you find out? Yes, you can find out, because the trajectories remain in that point. If we are starting from here, we are remaining in that point only. If you are starting from here, we are remaining in that point only. Okay, we are never leaving that enclosure or circle. So those we can call them as stable. Okay, so these kind of the stability, a system is said to be locally stable if the region epsilon is small. Okay, so this thing is, if this epsilon is small, then we can call it as a locally stable. Okay, so inside this particular region it is stable, outside it we don't know. It may be stable, it may be unstable, we don't know about that. Okay, so it is called as locally stable. Generally when we call it stable, it is locally stable. Okay, in terms of nonlinear systems. Now the next definition is asymptotically stable. Now remember, this definition is, it is asymptotically stable if it is stable. First it should be stable, and then as t tends to infinity, x of t should tend to 0. Okay, as t tends to infinity, x of t should be tending to 0. This is shown in this figure 18b. See here. So we are starting from a circle of delta, this. Okay, as time progresses, we may go outside or anywhere inside the circle of epsilon, but at the end we will reach a point t is equal to 0. At t is equal to infinity, we will reach a point x of t is equal to 0. 0, 0, that is origin. We will reach origin definitely. Then it is called as asymptotically stable. Okay. So also this R, another circle is taken just to check whether as t tends to infinity. See, we cannot look at the infinity. So we take a large time, let's say 10 seconds, 100 seconds, 1000 seconds, and check whether it has converged or not, just to check that. So it is like a 2% band you have for a settling time. It is like that. Okay, so a circle of R, radius R, is that band. So if it is if your system goes inside that circle in certain time, then you can call it as a asymptotically stable system. Okay, see, note that the singular points in the phase portraits figure 13 and 16a are asymptotically stable. We'll see which are those points. 13 is this, 13 is this, and as you can see, it is starting from anywhere but going towards 0 only. So this stable node is a asymptotically stable equilibrium point. Okay, and second one was 16b. Yes, this. So you are this is focus. Okay, focus means two eigenvalues on the left half of the S plane. So they will have this oscillatory type, but they will spiral towards the center. As you can see, if you start from this point, this will go towards the origin. All right. So this is also this point, this okay, not this 16a. 16b is unstable, of course. It is going outward. This I was talking about. Okay. So this stable focus point is also asymptotically stable point. Asymptotically stable equilibrium point. Okay. Yes, 16a, not 16b. Okay. The next definition, the third definition is system is asymptotically stable in large or globally asymptotically stable. In large means globally. If it is stable, it is asymptotically stable. See. Okay. Just these two conditions. There is no circle conditions here. The regions are not defined here. Okay. Even the initial, it could be anywhere in that plane. It could be anywhere. Even if it is starting from infinity coordinate, even from that, it should come back to origin as t tends to infinity. Okay. It is strictly stable. Then we can call it as a stable in large or globally stable. Generally, this is desired than only saying it is stable. Okay, this is the extra information, so you don't need to worry about the circles like is it stable in this region only, outside does it work? You don't need to worry about that. Okay, it is stable everywhere. Okay, so in large guarantees that every motion will approach the origin. Yes, in fact the singular points in the phase portrait 13, see, just we saw that figure 13 and 16a were asymptotically stable, but also they are asymptotically stable in large. They are globally stable. Okay, so you don't need to worry about the local stability of them. Okay, so you understood these three definitions uh, by word also, by graphically also. Okay, so we have seen them in the graphic representation also. Is there any doubt in these three definitions? Ask doubts if there are any doubts. Are there any doubts? Have you understood this? Don't be inactive. You can reply. In fact, you should reply. If you are not understood, if you are not even paid attention, you can say that, sir, please revise again. Is this understood? Gaurav has understood. Others? Shivanand, is this understood? Vishwajit? Vishwajit, is it understood? Shivanand?
हो सकते हैं बगल
Okay. See, if you even read these slides at your own speed, or just revisit this lecture again. Okay, I'm uploading them on YouTube. If you even revisit them, it will be clear to you. Okay. Also, these concepts are new to you. The general stability. When we say stability, you just say that yeah, eigenvalue should be on left half of S plane and it should be stable. So it was very simple in terms of linear systems, but it is not so simple in nonlinear systems. Okay, so it will take some time to make that space in your head. Okay, it will take some time. I understand that it will take time for you to understand, but you at least know what are the tools to understand this. That this material, if I read, then it should be clear to me. That confidence should be there. Okay. uh, so let's wrap this up, the this unit. Also, there is one point remaining, the linearization of nonlinear systems. We will see that in the next unit, unit number 5. Okay. So because that chapter is quite big chapter, so I added this linearization part in that also. Yes, Onkar, do you have something to say?
No, sir.
Okay. So there is one more concept called as limit cycles. Okay, this we have seen in the I think mass spring damper example, where there was nonlinear spring, and at a particular frequency, it was exhibiting that behavior. Okay, so generally terms like this, the van der Pol differential equation. This is a general form of equation. So if we consider this equation, it is nonlinear. You know that this is x square is there, or even if it is x into dx, then it is nonlinear. So because of this term 1 minus x square, it exhibits that limit cycle. Okay. See, we observe that van der Pol's equation has a damping factor of this, which depends on the x only. So the damping factor, which should be the parameter of the system, depends on the system variable. Variable is x, parameter are unchanging in an equation. So it depends on x. So it is not a like simple thing to understand how the system behaves. Okay. So it has positive values and those things. See, it behaves like this. So consider any point. Let's say you start at this point, then see, you are going this way, you are remaining in that only. Okay, you're not going inside. Let's say if you start at this point, where does arrow go? This way. So you are in that circuit only. Okay, consider this as a racing circuit for a car. Also, if you start from the outside, you come and do this circuit only. Okay, so this is called as, this region, this path is called as limit cycle. Okay, this is a stable limit cycle. Stable meaning, even if you start from inside or outside, you are reaching at that path and remaining there only. Okay, and this is an unstable limit cycle. See, what is unstable limit cycle? See, you leave the cycle from a particular point. See, here you are leaving it. Okay, at this point, or you may go, and the system is going towards stability, but it may leave also. So this is a dangerous thing. See, you might say that, sir, this trajectory is going towards origin, so it should be good. It should be a stable system. Yes, in this case it is stable. But there is also a possibility that this leaves outside. This leaves outside. So there are pretty much any point at which it may leave out or it may leave in. Okay. So this limit cycle is unstable limit cycle. This is a stable limit cycle. Okay. So these are some discussion on that. So generally, limit cycles are undesirable characteristic of the system. Okay, it may be tolerated if if its amplitude is within specified limits. So let's draw a circle here. If we draw a circle here of epsilon and call that, yeah, this is staying inside that circle, so this is a stable system. It is satisfactory. It is having satisfactory performance, even if it is keep even if it keeps moving in a trajectory, that whole trajectory is inside my specified limits, so it is okay for me. Okay, so that way these limit cycles are handled. Okay, so this is some more discussion. You may read this. Okay, you may even read this discussion. And there is one more method, describing function method. See, there are some limitations with phase plane method. Okay, this phase plane method has some limitations. So this is an alternate way of handling the non-linearities, describing function method. So in this, what you do, you basically try to convert the non-linearity, the non-linear part of that mathematical equation into a different function. Okay, you try to basically this, see, g1 is there, g2 is there, so you can say that this is linear, but there is a non-linearity n here. So this n is having a transfer function. Some it may be transfer function, or it may be some other structure, like if this, then this, else this. Okay, something like that. It may be multi-valued function also. It could be anything. So what you want to do basically is you want to convert this into a function that is easier to handle. Okay, so this is the whole treatment, like what is done there, and those things. You may read this in detail if it interests you, but basically we want to approximate that function as some other function. See, so this is a describing function. This whole thing is taken into the Laplace domain. So this en was replaced by this describing function. Okay, and it has, see, as you can see that this is nothing but output upon input. So gain of that function and phase of that function. So basically that non-linearity is converted to its a counterpart or a replacement which has its frequency response similar. Okay, but we will not go into this method much. See, there is some analysis we need to do. So this one, so what is done basically, so describing functions, generally the common physical nonlinearities, we have 5 nonlinearities. We find the describing function of for all of them. Okay, and if they are combined nonlinearity, then that describing function may be different. Okay, so this is generally the dead zone as well as saturation, where this d/2 represents your dead zone, and this part is saturation. Okay, so we wish to convert this into the its frequency counterpart. Okay, so this is the frequency response. So this is the output that we get if we pass a frequency, this wave from this, you will get this. So this you can see the peaks are clipped, as well as you get a amplifier type response here. I think type A, type B, that kind of amplifiers response you get. Okay, so that dead zone and saturation, this function is written here. Then for this you find replacement. Okay, for each region you find the replacement, you get a function. Okay, so you get see, this is only for saturation, this is only for dead zone. If you combine them, you get a function. So that whole function is called as a describing function for dead zone and saturation. So this way you can basically represent that system into a frequency counterpart, but we will not uh, uh, see it deeply, like we're not going to discuss it with detail, the describing function method. Okay, so this completes your unit number 4, nonlinear system analysis. Not unit number 4, I think unit number 3 it is. First one is introduction to state space. Second one is state space design. in which we have seen controllability, observability, state feedback controller, and observer. Third will be this nonlinear system analysis. Fourth will be the Lyapunov theory analysis. Fourth, and fifth will be the PID controller. Okay, that we took early, the PID controller part. But yes, this is done. I think 5 units will be done. Fourth unit is still remaining. The whole fourth unit is remaining. Okay. Now let's talk about the assignment. Assignment number, I think 6 it is, right? 6 or 5. Yeah, 6. So assignment number 6. Also assignment number 5. Where it is? Assignment number 5. Okay. Assignment number 5, 14 people have not submitted it. So you have to do it. Assignment number 6 has 4 questions. What are the common physical nonlinearities? Explain each one in detail. So we have discussed this. Second question is how nonlinear system differ from linear systems. This answer you will not find in these slides. Okay, you may read some initial 1-2 slides, or you may go and read this 15th chapter in Nagaraj Gopal book, or you can search online for different resources. Okay, don't do copying from each other. These answers should be different. Okay, you may write this as one page, or some 3-4 paragraphs are also sufficient. Okay, but that answer should contain like how they are different from the linear systems. What are the characteristics that that nonlinear systems possess that linear don't have, or linear possess that nonlinear don't have? So you can do a difference kind of thing. This it is present here, it is not present here, that kind of thing, difference table, or you may write it down. Okay, so it is anyway. This is a good exercise to for you to understand how nonlinear systems are different from linear systems. Third question is explain different types of singular points with graphs. This we saw in the last lecture, in the third lecture. Okay. Now the last question is explain the procedure to linearize a nonlinear system using Jacobian matrix. How to determine stability of that system. This is yet to be discussed. Maybe in next week, start of the next week, we will cover this part. Okay, in the next unit we are going to cover this. Then you come back, write the answer for this, and then submit. All right.